Now, to find antiderivatives for more complicated functions, there's some rules for antiderivatives, just like there were for taking derivatives. For example, the antiderivative of the sum of two functions is the same as the sum of the antiderivatives. So you can break up antiderivatives over sums, and you can do the same thing over differences. The antiderivative of the difference of two functions is the difference of the antiderivatives. And also, there's a constant multiple rule. If you have a constant multiplied by a function, that constant can be factored in front of the antiderivative. I'm going to illustrate all of these with examples in a few minutes. One thing I want to emphasize right away, though, is that there are no simple rules for products and quotients. The antiderivative of a product is not the product of the antiderivatives, and the antiderivative of a quotient is not the quotient of the antiderivatives. So we're going to X these out and write no. Those would be very, very bad mistakes to make on a test. So for some beginning examples, first of all, let's do this one. Let's look at the antiderivative of 3x to the fourth minus 5x to the sixth. First of all, I'm going to apply the difference rule because I see the difference of two functions inside. So I could break this up as the antiderivative of 3x to the fourth minus the antiderivative of 5x to the sixth. So that was the difference rule. Next, I have a multiple of 3 in this first antiderivative, and I can factor that 3 in front. And in the second integral, I can factor out the 5. So that was the constant multiple rule. And then I can apply the power rule to each of these antiderivatives. So I have 3 times the antiderivative of x to the fourth is 1/5 x to the fifth minus 5 times the antiderivative of x to the sixth. Adding 1 to the exponent, I get x to the seventh, and then divide by the new exponent. Notice when I have a sum or difference like this, I only need to add 1 plus c at the very end. So simplifying just a bit, 3/5 x to the fifth minus 5/7 x to the seventh plus c. Now something that by the way, that was the power rule. Something I fully expect is that with a little bit of practice, many of you are going to be skipping from the original problem directly down to this. And it's going to be fine to skip steps. As soon as you can skip steps without making mistakes, go for it. Now let's look at a couple of more examples. So write this down real quick if you need to. Pause the video. I'm going to erase it. Let's look at the integral of x squared times x cubed plus 1 dx. I'm going to change color for a moment because I'm going to start by doing this wrong. So I'm going to make a note. This is wrong. I don't want you to learn to do it this way. But this is a common mistake that I see. People will find the antiderivative of x squared and multiply it by the antiderivative of x cubed plus 1. The antiderivative of x squared is 1/3 x cubed. The antiderivative of x to the third plus 1 is 1/4 x to the 4th plus x. And then you could distribute to get 1/12 x to the 7th plus 1/3 x to the 4th plus c. Now think about that. The way that you can check your answer for an antiderivative is to differentiate what your proposed answer is and see if it gives you the original function. If you differentiate 1/12 x to the 7th plus 1/3 x to the 4th, does that give you anything resembling x squared times x cubed plus 1? Not at all. So there is no way this can be right. Somebody who made this mistake, what mistake were they making? They were trying to use a product rule for integrals. And remember, there is nothing like this. When you're integrating a product, you cannot just integrate each factor. So now let me show you the right way of doing this. The trick is to simplify what's inside by distributing. If I multiply x squared times x cubed plus 1, I get x to the 5th plus x squared. And then I can just find the antiderivative one term at a time. The antiderivative of x to the 5th is 1/6 x to the 6th, and the antiderivative of x squared is 1/3 x cubed. And notice that that's very easy to check, and it doesn't look very much like this at all. So for a couple more examples, I'll put one in down here. If we have the antiderivative of 5x to the 7th, if we wanted to do this carefully, step by step, using the rules over here on the left, we would use the constant multiple rule to factor the 5 out. Then we'd use the power rule to find the antiderivative of x to the 7th, which is 1/8 x to the 8th. And then we could simplify 5 times 1/8 is 5/8. What you're probably noticing, though, is that when I integrate a term that looks like 5x to the 7th, but I'm adding 1 to the exponent, adding 1 to 7 to get 8, and then I'm dividing the coefficient by the new exponent. So for me, it is perfectly fine if you skip these steps. So for example, if we want the antiderivative of 3x to the 6th plus 4x squared plus 2, it's fine with me if you simply go term by term, add 1 to the exponent, divide by the new exponent, so 3/7 x to the 7th, plus, add 1 to the exponent 2 to get 3, divide by the new exponent. And then last, remember that the integral of a constant with respect to x is the constant times x. And of course, it's easy to check your answer just by differentiating this. If you differentiate your proposed antiderivative, you should get this function that you start off with.